Okay, so today we are going to be talking about momentum. So, what is momentum? Momentum is defined through an equation. We'll call it P, which will be our momentum, equals m, which is our mass, times our velocity. So, P equals mv. That is our equation for momentum, where P is our momentum, m is our mass, and v is our velocity. Okay, so let's see if we can work through just a couple of small examples for this. So if we were to find the mass of a football player, or the momentum of a football player, knowing that his mass is 100 kilograms, and his velocity was 10 meters per second. So what would the momentum of this football player be? Well, all we would have to do is take the mass, multiply it by our velocity, and we'll get our momentum. So P equals 10 meters per second times 100 kilograms, and that will give us 1,000 a momentum of 1,000. Now, the units for momentum are a little bit weird. They're going to be kilogram meters per second. So, kilogram times meters per second. So, the momentum of a football player moving with a velocity of 10 meters per second who has a mass of 100 kilograms will be 1,000 kilogram meters per second. Alright, so with that being said, if that is our definition of momentum, let's take a look at a very similar equation, or a very similar definition. So, there is this idea of impulse. Impulse is force over time, or force multiplied by time. So impulse equals force times the change in time. So we might call this force times delta t, and all this is to say is the final time minus the initial time. It would be the change in time. A lot of times it would be fine to write force times time, but I think this delta is important. And again, all this means is, let's see, delta t equals t final, the final time, minus t initial, the initial time. So, with that being said, we also have the impulse, which I think I'll just call impulse. I'll represent it with a J. So our impulse equals the change in momentum. So with that being said, again, I'm using the delta notation again. All the delta notation means is the final momentum minus the initial momentum, or whatever value we put here. So the impulse will be equal to force times the change in time. It's also equal to the change in our momentum. So let's think this through just a little bit. We can replace this P with mv, and so it will be the change in our mass times velocity, And so we can use our what we use delta, our definition of delta, where basically this would be our mv final minus our mv initial. And since our mass is constant, really we can take it out from there and we just have our m v final minus v initial. So it'll be our mass times the change in velocities will be our impulse. So let's see here. If we have an official Major League Baseball which has a mass of 0.14 kilograms, and a pitcher throws a 40 meter per second fastball, which is hit by the batter straight back up the middle at a speed of 46 meters per second. What is the change in momentum of the ball during the collision with the bat? So, let's see here. So we have a fastball is being thrown. It has a mass of 0.14 kilograms. It is being thrown at 40 meters per second. And after it is hit, so this would be our part 1, and our part 2, it's being hit backwards with a velocity of 46 meters per second. So we want to know what is the change in momentum of the ball. So what is the impulse of the ball? So simply by using the equation that we found earlier, all we need to do is take the mass of the ball times the final velocity minus the initial velocity. Okay, so here it's important to pick which is forward and which one's backward, because since these are two opposite directions, one of these needs to be positive, one of these needs to be negative. It doesn't matter much on which, but let's call the rightward motion positive, leftward motion negative. So that would be mass. Our final velocity will be negative 46 meters per second. I'm going to suppress units just to kind of make things look a little clearer. And we'll be subtracting from that 40 meters per second. Again, I'm going to suppress the units. And so that will be all multiplied by our mass. So we can rewrite this as 0.14 kilograms. Now, and again, I guess I'll suppress that as well. Negative 46 minus 40 would be negative 86. And so the change in our momentum would be 0.14 times negative 86. Let me run through, grab a calculator on that. So 0.14 times negative 86. That gives us negative 12.04. Okay, so this would be a way to approach and solve this type of problem. So if we were to work through something similar to that, if we had a 10-pound bowling ball, and let's see, so we roll it down to strike some pins, and let's say instead of 10 pounds, let's call it 10 kilograms. And we roll it at 3 meters per second. And when it strikes the pins, it keeps going. But after it strikes the pins, instead of going at 3 meters per second, let's say it starts going at just 1.5 meters per second. So, how would we find the impulse? Well, we know impulse equals mvf minus vi. So what we can do, and really quick, remember, this is not only impulse, we are also solving for and finding the change in momentum. So all we need to do is find the values to fill this out. So m is going to be 10, v final is going to be 1.5, and v initial is going to be 3. So we can write this out farther. We get negative 1.5. And finally, we have 15. And remember, like, if you suppress units like I have, always remember to throw them in at the very end. So we would have kilogram, meters per second. Okay. So, with that being said, a quick little discussion on bouncing, and really we've already kind of seen it in action. If you want to cause the largest change in momentum to an object, if you want to impart the largest amount of impulse, the largest change in momentum, you don't want to simply take and stop an object. You want to stop it and then reverse it. You want it to bounce back. So that's an important thing to think about. And the big reason that's so important is, well, remember to keep your directions. Consider your directions. If we have a ball going this way at 4 meters per second, it hits something and bounces back and goes back this way 4 meters per second. If you don't take into account the direction, you would get that this hasn't changed its momentum any, when it's changed its momentum quite a bit. So always keep in mind the direction change and what happens when a bounce occurs. You should always expect a bounce to have a greater change of momentum than if you just simply stopped the object. So, with that being said, another small thing to think about is kind of just a few different cases with this change in momentum. So, we know that impulse equals our F delta t. And so, just by looking at this equation, there's a few things we can kind of tell. If we have a constant impulse, so let's say, and that's pretty standard, if we know that, let's say, a car is going to run into us and it's going to come to a complete stop and striking us, we know that impulse, that change of momentum for that car, is going to be constant because it has a mass, its velocity went from whatever it was to 0, so its change in momentum will be constant. So no matter what, that value of j will have a value. We can decide how we want to basically get to that value, how we want to distribute the value across our force and our change in time. So if a car runs into me and I'm in my car, I would really like to make that force as small as possible. So I would like to have a small force and a really big change in time. And so we actually see this in like modern car safety, where cars are designed to crumple. And the reason they crumple is it slows down that impact and makes the impact take longer. And since the impact takes longer, there's less force. Force leads to acceleration, and acceleration is what causes a lot of bad things and wrecks and stuff. So we can examine this impulse equation, this J equals F delta T, to come up with some interesting things. If for example, we want to, maybe we want to throw a punch that completely, does as much damage as possible if we're like boxing or something. We really would, if we have a determined impulse, we would want the time of contact to be as low as possible. Low time of contact, high force, more damage. So that's just kind of some different ways we can just look at this equation and get some interesting information from it. Okay? So with that being said, the other thing that I think is important to think about is there's this notion that momentum is conserved. We have a law of the conservation of momentum. And so that law states, in the absence of an external force, the momentum of a system remains unchanged. This is to say that if there's no external force, the momentum in one state is the same as the momentum in another. So, this is, without any external forces, this will always be true. Now, this might seem a little, maybe easy and obvious, maybe unapproachable. So, let's think of a few examples that we can use to really kind of give some flesh to this relationship. So, let's talk about collisions. Collisions are examples where two objects or more come together, strike, and then they do something. Maybe they go off together, maybe one stays stationary and the other shoots off in a direction. Either way, collisions are where objects collide and move before and after that collision. So, let's see. 1 second. Okay, so we have two different types of collisions. We have elastic collisions and inelastic collisions. Elastic collisions are collisions where, so let's see. Elastic collisions are collisions where objects will strike each other. So if I have ball 1 and ball 2, ball 1 comes and hits ball 2, and then ball 1 might be stationary and ball 2 might now be moving away from ball 1. So the big thing with elastic collisions is ball 1 and ball 2 can't be deformed or anything like that. They can't lose pieces. And the other thing is heat can't be generated. So really something that I'm only going to mention, it's not something that is very important right now, but what makes an elastic collision is we know that in every collision, the change in your momentum is going to be 0 because of the conservation of momentum. But for elastic collisions, and again, this is something that we will not really get into very much right now, but it's kind of important to say the kinetic energy of a elastic collision will not change either. And that is kind of seen in this entire, we don't have any object being deformed, we don't have any heat being created. So in an elastic collision, the kinetic energy will always be the same. A inelastic collision still has the requirement that the change in our momentum is 0, but here our kinetic energy, it will not be 0. And so in an inelastic collision, we have ball 1, it's going at ball 2, and then we actually have in our second state, ball 1 and ball 2 have combined and are now moving together in some forward direction. So with that being said, let's consider one or two questions for elastic and inelastic collisions. So, if I have a ball, or actually let's say two blocks, okay, so block 1 weighs 2 kilograms, block 2 weighs 3 kilograms, and block 1 is moving at block 2 with a velocity of 3 meters per second. Okay, so let's see here. If in block 2 is going to be stationary. So what are the momentums of our blocks? Well, we have the first block has a momentum of 2 times 3 kilogram meters per second. And again, I'm going to suppress units for the rest of this. So really, 2 times 3, and the momentum of the other block is going to be 3 times 0. So if we want the total momentum of the system before the balls collide, or before the blocks collide, my apologies, we would get 2 times 3 plus 0. And we know that since momentum is conserved, this initial state, these initial momentums are going to be equal to the final momentums, or the momentums after the blocks collide. And so that would be the momentum of block 1. So we would say maybe B1 plus B2. Okay, so with that, we have for inelastic collisions, the kinetic energy will be 0, and for this case, I think I would typically give you that B1 is going to be 0. That at the end of this collision, I'm going to say that my B1 comes to a complete stop. Now, with that added little bit of information, we should be able to find the momentum of B2, the momentum of the second block after the collision. So, with that being said, we multiply 2 times 3, get 6, equals B2, really. And so, now we can, typically we'd probably want to solve for something like velocity, and we can do that. We would just have 6 equals my mass for B2, which is just going to be 3 times the mass, or times the velocity of B2, and so we would find the velocity of B2 equals 2. Okay. So, with that being said, the last thing that I'm going to talk about is our inelastic collisions, and these, especially collisions in which the two initial objects come completely together, we should be able to solve these. So if I have two blocks, 1 and 2, this weighs 5 kilograms, this weighs 12 kilograms. If this is going 2 meters per second, and this one is going 1 meter per second, we should be able to see what the velocities are and the momentums after they collide, provided they come together and merge. So if we take those two, they collide, we get a 1-2 block with a mass of 5 plus 12. We should be able to find the velocity of this block. So let's do that. Let's write out our momentums. So P1 plus P2 equals P12. This is just saying the momentum of this block plus the momentum of this block will be the same as the momentum of this block. And that's just using the conservation of momentum. So we can now use the formula for momentum to say 5 times 2 plus 12 times 1 equals the mass of both, so that would just be 17 times the velocity of my 1-2 block. So now it's just simply solving for this v1-2, and so I would just run through and get that. So 5 times 2 is 10, 12 times 1 is 12, so plus 12 equals 17 v1-2. Now it really is just simply walking through these steps, solving for my v. And so finally, we're left with the velocity of that block equals 22 over 17. So if we want to, we could even go one step farther and get this as a mixed number. We get 1 and let's see, 5/17. And that seems reasonable, really. The velocity of this is 2, the velocity of this is 1. We would expect the velocity of the total to be between the two. So, this is making a good deal of sense for our velocity. And always remember to throw on your units at the end. Okay, so hopefully everything in this section made sense. If you have any questions at all, please feel free to ask them. With that being said, really that's all I want to cover on this. So hopefully this helped explain momentum, impulse, and collisions. If you have any questions, please let me know.